Hello everyone, my name is Joe, and here's the long overdue but much requested video of me explaining the three-body problem. Now I'll try to do everything all in one take, so it's kind of like having a conversation with all of you. But please feel free to move around and skip around the video because there will be some things that you guys probably already know about, and I don't want you guys to spend too much time on those things. But let's start with a demo first for those who are new here. So what this project is that I aim to search for periodic trajectories in the three-body problem that's known to be chaotic. So here's the demo. The left side, oops, sorry about that. The left side is the heat map of all of the points, and on the right side we have the actual simulation. Now see, this one that I gave is periodic and repeats over itself, having a nice infinity symbol, a little bit sideways. You can see it repeats itself. So that's the end result that we're hoping to get, and I'll go over how we got there. I'll start with an outline. There's three main sections that we're going to cover here. The first one is the physics, so simple going over how I made the simulation of the three-body problem. The next one is chaos theory, and this is about the quantifier for quantifying how chaotic this system was. And lastly, it's the methods. How did I convert this 12 vector, or actually, I think it's 15 vector system into 2 vectors into this heat map? So that's all that's going to be covered for today. It is a lot, so again, please feel free to skip around. Let's begin. So let's start with the physics first. All of the things in this simulation are covered with Newton's universal law of gravitation. I just searched it up here. Very ubiquitous. It's the same one I've written down here. And we're going to use that to get the acceleration for each of the planets or bodies. And I'll go over a little bit of the code, as that might be interesting to some of you. There's a class called system, and each system stores a few bodies. For us, we have 3 bodies. Now each body will have this acceleration function where it computes the extraction it has on the other planets and combines that all together to get an acceleration that's a vector. So imagine you can have a body and another one and another one. So for this body, what it'll do is look at this one. What's the attraction here? What's the attraction here? And at the end, it might sum up to a vector that maybe goes here. That might be where it's going to go at the end. So that repeats for every single body, and we have multiple iterations to get the next step of the system. And then it'll iterate through that and animate the next frame. Now, we use something called an integrator for this because the three-body system is not solved. So that means I can't just input a time in the future and have it return the different positions. I have to go step by step, right? Imagine this planet, I gotta figure out the next, and continually to numerically integrate it. There's different numerical integrators, and most of the time you are sacrificing accuracy for a decrease in the efficiency, or it just takes more computational power to get accuracy. So you have to find a nice balance. And one of the most important things for this project, at least, is to make sure that it is accurate. And now to do this efficiently, there's something called a symplectic integrator. Now what this does is effectively just conserves the energy that's used, or not used. It just conserves the energy of the system. So there's nothing too wonky that happens with the system, and none of the trajectories will fly off really far. And the one I used is called the velocity relay integrator. I'm not going to go over it too much here, but just keep in mind that there are integrators that may be more suitable for you than others. And yeah, if you guys want to read about this one, there's Wikipedia articles. Just search velocity relay integrator and you'll get it. And then, let's see, what is next? Oh, one of the bigger things that I think is important that I included is something called softening. So what this does is, imagine you have 2 orbits, or 2 planets, very close together, and as they go on with each other, this gets attracted to this gets attracted to this. That was not a very good diagram, but they get closer together, and eventually they collapse to a singularity, and then the gravitational law, because it's inverse law, right? You can see this R undervalue start to decrease, right? That means the entire force increases a lot, and this body will get flung super, super far. And that's not what you want, because that increases energy. So you use something called softening. What this does is it kind of gives a maximum force that you're able to feel, right? And then I think the reason why one of this is an issue in the first place for the simulation is the fact that there's no collisions. So they can collapse to a singularity. Whereas in real life, you know, when you put the sun and the earth together, they're going to make an explosion. Although a little one compared to the size of the sun, but still something will happen, as opposed to here where they just get closer and closer together and then one gets flung away. So softening is definitely something to look at if you're going to try and do this too. So hopefully that concludes our overview for the physics, and you guys are understanding how to do that, and hopefully you guys can carry that away to make your own n-body problem simulation. But now let's go on to the next and more interesting part of this project, the chaos theory. How are these colors, these beautiful colors, generated? What made this part dark and this part red? So that is a quantifier for the chaos, the degree of chaos within the system. Now there's two methods I approached this with, and one ended up being better than the other. They are the Lyapunov exponent and the proximity function. Now I'll tell you right now, this one worked a lot better for me. So I think I'll go over it first since it's more intuitive as well. But to begin, we have to figure out something and understand something called phase space. Phase space, let me write that down. Phase space, like this. So what that is imagine that that looks like an E. Phase space. Yeah, imagine it as a multi-dimensional space. I drew a ball as an example during the cut, but it's a multi-dimensional space that stores the variables of the system, each variable in each of the axes. So imagine one of these bouncing balls will have two variables. It will have position and momentum. Whoa, don't they mean, oh yeah, momentum is mv. So the position, actually isn't position D. D is better for position, and mv is momentum. That's a little messy, but yeah, position and momentum, and then they are going to be two axis. And then imagine as the ball bounces, I don't know, something with the position as it bounces through the balls, through the walls, up and down, it moves through phase space in a certain way. So that's kind of how the trajectories in phase space work. Now for our own system, it'll be a little more different. It's a little more complex than just two variables. Our system actually has 15 because there's like X and Y, and for each body, I'll go over more of that in the next section, but it's a very complex system. And then as it goes through phase space, it's not two-dimensional anymore. It's 15 dimensions. That's a little hard to get our human heads around. So instead, we're just gonna visualize these methods with a 2D plane on the surface. So I'm gonna start with this one. Now, let's just pretend the trajectory is periodic. So it starts at a certain point, and then it starts to loop. Boop. And it goes to a point that's really, really close to where it started from, right? Of course, it starts continuing to grow, but it does reach a point where it's really, really close. And we'll call this distance dx. And I did question mark because you don't know where that is yet. And this point is the closest that will be. So it's the proximity function, or what the proximity function returns. Now, this is different for every single system. Some systems might just never come back, so its proximity is super far. And then that will yield you how periodic it is. Why so? Well, because if a system, let's look at our initial demonstration, this ball, it got really, really close to where it started. So its return will be very, very small. As opposed to if I had a ball here and it just flew away, it doesn't really get close to where it was, right? So the lower this value returns, the more periodic it will be. And then using that, we get the different colors here, right? See, this axis is called proximity, and the lower it is, darker region it is, the more periodic it is, which is what you get here. Now, let's go over the other one, which is which one I started with. You can skip this part if you want, but it's also good knowledge. It's called the Lyapunov exponent. So what this does is it measures the sensitivity of initial conditions. So it kind of does the converse of this. It instead measures how chaotic something is. And the way it does this is, imagine somewhere in phase space again, and we have two initial conditions that start very, 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 very close together. They're like touching almost, but they're not actually touching, but they're almost. And then as you evolve through phase space, they begin to separate. One takes one route, the other takes the other, and this distance begins to grow. Now, you can model this with an exponential function. So you imagine the distance that they go start to go up, e to the lambda, right? And we can say the distance at some point final, so like here, is equal to e to the x of the initial, so x0, x0. And then so you model it like this. It's growing, it's an exponential growing. And then this is the key part. The Lyapunov exponent is this, right? That's the exponent. Well, what can you get from this exponent? Let's see. Well, the bigger that this exponent is, the faster it'll separate. Whoa. The more chaotic it is. The smaller it is, if it's like 0.001 maybe, it'll look something like this, depending on the axis. So it'll be less chaotic or more periodic. So it'll return something similar to this, and we'll have lower spots being more periodic. But this just ended up being better because there's less computation required. It's really straightforward calculating this number. As for this, you actually have to do some averages, some other things, moving this trajectory once in a while, and you're calculating two systems at once. So it just took more computational power. So this one was the way to go. I think that's a wrap for the chaos theory, at least. So now we're going to go over the implementation and the methods, which is also really cool. So yeah, let's start with this. Now, before I talked about this whole system being a 15 vector system, but you notice this is two-dimensional. I do not see 15 vectors in here. How did I do this? Well, I didn't really do it. I looked at somebody and said, wow, that was cool, and kind of copied them. There's a few things to do. Firstly, we have to notice that my system has a lot of simplifications. It removes like spin, all of that stuff. I'm going to try and remove these, what do you call it? Oh man, vectors or variables one by one and see how I simplified to this. So first thing, I made it 2D, not 3D. So that already reduces one axis. And the other is I made all of their masses the same. So that just no longer becomes a variable. And then we start to get to the part where it's kind of taking a shortcut and missing some periodic trajectories. Firstly, we're going to rely on the fact, I'm pretty sure I interpreted this correctly. Newton said this, all periodic trajectories go through a collinear configuration, meaning at some point they all form a straight line for the three-body problem. So I kind of utilize that. So then there's no longer an initial y, I guess you could say. They all are on this line, and then eventually it just becomes d1 and d2. How far away are they from this middle? And then I just decided this distance should be the same, so that no longer becomes a variable again. And then the next part is their velocity. Now, this whole system still has a 6 variable system. So you have x, y, x, y, x, y for their velocity. But what I wanted to do was conserve momentum. That means I want the net momentum to stay in the middle so that this animation is always centered. How do I do that? Well, since all of their masses are the same, as long as their velocities add to a net zero, they will return a steady and equilibrium momentum. So what I do is I take the middle and call their velocity v1, and the other two, I'll split the middle in half and call v2, and they go in the opposite direction, where eventually they will sum up to a net zero for the momentum, leaving the system in stability. So now we kind of have a system, and we see the only thing that kind of dictates this system in the beginning, d1 is held constant for everything. The only thing that changes is velocity, right? But it's in 2D, right? So we have vy and we have vx, right? Like that. And so those are the two initial conditions really. And we can see that in one of the data files here. I have the full entire map. So let's go up to the top. Right, we have D, which as you can see is always 1, and we have Vx, Vy, and the proximity that it returns. So you see Vi gradually changes, and of course so does Vx some point. Yep, change row by row, and that gives a proximity function at the end. So that's how you get this heat map at the end of all of this. You see that it does that. And yeah, I'm gonna give this nice trajectory. I think my voice is going out from talking so much. Let's see, where am I now? I think that's about it for talking about all of it. There's a lot of code to cover actually, but I think I'll go with some demos now for other things. One of the things is that I really liked about this whole thing is the fact that I can zoom in, but wait, we see it's a little grainy, right? What can we do? I'm gonna press Q, so it'll quit, but it'll give me a zoomed in version of what I just did. So I guess this is not the best example because you can't really see that it's zoomed in. You kind of just see that it's a messed up version, but I'm gonna restart the thing. Thank you for your patience. I'm gonna zoom into an area where you would definitely notice, whoa, he enhanced that. So maybe like, oh, this guy looks like it'd look cool if I enhance it. Let's press Q over there and then enhance, like so. That looks like an enhanced version of the old image. Wow. And I'm going to keep zooming in. Zoom in, boop, and press Q again. And what I want to end up with is finding a place that's a dark spot. Sorry about the finger there. Oh, wow. That's a cool pattern. I think that's a cool pattern. And there's many of these. So I'm not too surprised. Although the first time I saw this, it was very interesting. Okay, so you can see the value returns here. And through experience, 0.23 is not great. As in the periodic trajectories are not too periodic. So I'm gonna go a little crazy and zoom in a lot more. See what this returns. Okay, I guess it's not that dark, but okay, let's just see what one of these dark regions give. 251, how periodic is this? Loops. Oh, we see something, maybe. No, it's not very periodic. I don't think that was a great demo to begin with, but you guys saw the ones at the beginning. That was not bad at all. So I think that concludes this 3-body problem. I hope that was a good watch for you guys and you guys learned something insightful. It is my first video, so hopefully you guys can give me some good feedback on what to do next. I really like the fact that I don't have to edit too much because I think that would take a lot of the time. But for those who have followed along and watched all the way till now of this almost 20-minute session of me talking, I'm very thankful for you guys. Hope you guys enjoyed, and I'll catch you guys on the next one, which will probably be the double pendulum. See you guys.